Welcome back, dual credit students. This is the next section, section on end behavior, or as your book calls it, limits at infinity. I like to think about it as being limit as x approaches infinity. But what we see here, I've got it titled, you can think about end behavior as being x approaching infinity of a function, or even x approaching negative infinity. In other words, what's happening as our domain's getting infinitely large, or what's happening as our domain would be getting infinitely small. So it could be something along the lines of, well, that's beautiful, of this. So what are the tendencies? And the thing about this is all of these graphs here have one thing in common. All of these graphs are increasing from 0 to infinity. But that's really where the common themes end in these problems. This problem right here is increasing. It's probably going to increase forever. Let's think about this as being the square root of x, possibly. So I will need to erase that. So if this is the square root of x, it will get infinitely large, but it's getting infinitely large at a rather small rate. Then you have a situation like this. This one's getting infinitely large, and it's getting infinitely large really fast. So both of these would have limits that do not exist, or limits that we could say are in infinity, because they both will eventually get to every range value. But in a case like this is where we're going to have something called a horizontal asymptote. Here we have a situation where, yes, we are increasing, but this graph here is getting closer and closer to 0 the farther out we go. So, what an equation can we look for to see what's happening here? How are we getting closer and closer to infinity? Well, all right, I think Soup here hid my eraser on me. All right, here it is. So, I'll clean this off real quick. And let's look at an example problem. And we're mainly going to look at this in terms of rational expressions. Rational expressions are the ones that really get neat as far as discovering what's happening as values grow infinitely large, or, as I said, grow infinitely small. So let's say that we want to know what is the limit, and I'll do infinity here, of x squared minus 2 over x plus 3. Well, if we look here and think about what's happening in the numerator, and you think about plugging in numbers like 10, 100, 1,000, and so forth, and 1,000's not a big number at all. 1,000,000's not a big number. When you're talking about this value of, or this concept of growing infinitely large. So, but let's just pick a number like 10. Okay, if we pick 10, we get 100 minus 2, which would be 98. And then we would get 10 plus 3, which would be 13. So you've got 98 divided by 13. That's a number that is going to be less than 10. I'll even get us an exact estimate. That's kind of funny to say. I'll get us a decimal approximation. So we've got 98 divided by 13, and that is going to be approximately 7.5386. All right, now let's talk about 100. Okay, so 100 squared would be 10,000. 10,000 minus 2 is 9,998. And then over 100 plus 3, which would be 103. And we do that arithmetic, and we get 97.0680. So this number is a lot larger than this number, and we see the farther out we go, the bigger the number gets. And again, We looked at 100, we looked at 10, but as we plug in, notice just that both the numerator and the denominator are growing. It's just that the numerator is growing so much faster than the denominator is. So this function right here will get infinitely large. Now, we looked at 2 examples earlier. How infinitely large are we getting? Well, we can actually use synthetic division here to get an approximation of how large it's getting. So we could go with, all right, let's take -3 and let's divide it into 1, 0, and -2. Again, x squared, there is no linear term, so we have the 0 in its place, and then we have the -2 here. Pulling down 1, -3, -3, 9, and the remainder here is not important. What we see here is that it's getting infinitely large, but it's getting infinitely large at a pace of x minus 3. So what we would see here is we would have what's called a slant asymptote. And the slant asymptote is this line x minus 3. And it would possibly be doing something like this. Or it could be doing something like this. I don't know what the case is in this case. But it's growing infinitely large along this pattern here. So that's an example. And we'll talk about the commonality in it in this case. But the thing you need to look for is, hey, the numerator is growing faster than the denominator. And any time in fractions that numerators grow faster than the denominators, there is no bound to how big the y value will get. Therefore, we would say that the limit as x approaches infinity here is infinity, but it grows to infinity at a rate of y equals x minus 3.